Dear students, welcome to class of Topology. In this video, we are going to follow the textbook K.D. Joshi, General Topology, second edition. So, before defining the topological space, we see what are the properties of open sets in metric spaces. So, when you have a metric space XD, okay, what are the open sets in metric space? When A is a subset of metric space X, we say that A is open if all of its points are interior points. Basic examples are empty set is always open set with respect to any metric. Empty set is open in any metric. Similarly, the full set X is always open. And another important property of open sets in metric space is when you have two open sets E1 and E2 are open, then their union E1 union E2 is open. Or you can take any union, any number of elements, their union is also open. That means we know that arbitrary union of open set is open. Arbitrary union of open sets is open. Another property is when E1 and E2 are open, we have E1 intersection E2 is open in the metric space XD. What about their arbitrary intersection? It will not be open. But their finite intersection is always open. So E1 intersection E2 intersection etc. intersection some En for any finitely many n, it is open. So the properties of open sets in a metric space are some important properties are empty set is always open, full set is always open, the union of open set is open, and finite intersection of open set is open. Okay. Now let us consider let XD be a metric space. I take a collection tau as collection of all A subsets of X such that A is open in X with respect to the metric D. Okay, then what are the properties the collection tau have? Clearly we know that empty set is always open, therefore empty set belongs to this collection, and full set is always open, therefore full set belongs to this collection. And I can say that tau is closed under arbitrary union. Because when you take collection U alpha belongs to tau, which means each U alpha is open in X. Since X is a metric space, there are arbitrary union of open set is open, therefore union alpha U alpha is open in X. When some set is open in X, it will be belongs to tau because that is our collection tau. So which implies union alpha U alpha belongs to tau. Therefore tau is closed under arbitrary union. Fourth one, tau is closed under finite intersection. Tau is closed under finite intersection. Why? Because when you have a collection of U alpha belongs to tau, which implies each U alpha is open in X as a metric space, then any finite collection of intersection of this U alpha is open because finite intersection of open set is open. So intersection I equal to 1 to n ui is open in X, which implies intersection I equal to 1 to n ui belongs to tau because when the set is open in X, that will be automatically belongs to tau. So what are the properties tau have? Empty set belongs to tau, full set belongs to tau, and tau is closed under arbitrary union, and tau is closed under finite intersection. And what is this tau? It is nothing but collection of open sets in the metric space XD. Now we are going to generalize this idea of open sets. Next definition is topological space. Topological space. For that, I take let X be a non-empty set. Okay, and what is a topology? Topology is a collection. I denote it by some tau. Okay, it is a collection of A subsets of X. Topology tau is a collection of some subsets of X with the following properties. With the properties: 1. Empty set should be belongs to this collection. Second one, X, the full set should be belongs to this collection. Third one, which is same as the properties of open sets in metric space actually. Arbitrary union of members in tau belongs to tau. That means I can write it as tau is closed under arbitrary union. And fourth one, tau is closed under finite intersection. When this collection satisfies all these four axioms, we say that tau is a topology on the set X. When tau satisfies all these axioms, we say that tau is a topology on X. Okay, then the pair X tau is called topological space. Topological space. So what is a topological space? It is a non-empty set together with some topology on it. Or I can say that a non-empty set together with some collection of subsets of itself. Right? Okay. Now we will see some examples of topological space. Examples of topological spaces. So one important example is discrete topology. Discrete topological space. Okay. So what is a discrete topological space? I take X as a non-empty set itself. And tau is nothing but collection of all subsets of X. I take all subsets of X. So that is nothing but the power set of X. I take tau as all subsets of X, that is power set of X. Then we can easily prove that this power set of X form a topology on X. For that we need only verify 4 axioms for the topology. So first one, empty set. We know that empty set is a subset of every set. Therefore empty set is a subset of X. When it is a subset of X, tau is a collection contains all the subsets of X. Therefore empty set will be belongs to tau. And what is second one? We know that every set is a subset of itself. Therefore X is a subset of X implies X also belongs to tau. Okay. And third property, tau is closed under arbitrary union. That means we take some collection of sets from tau. Let collection U alpha are members from tau. What it means? Each U alpha is a subset of X. When each U alpha is a subset of X, union alpha U alpha is also a subset of X. So which implies union alpha U alpha belongs to tau. When it becomes a subset of X, it also belongs to tau. Right? And the fourth property, tau is closed under tau is closed under finite intersection. So for that again we have collection U alpha as a members of tau. Collection U alpha is member from tau. Then each U alpha is a subset of X. Each U alpha is a subset of X. Then you take intersection I equal to 1 to n U alpha I. It is always a subset of X because if A and B are subset of X, A intersection B again subset of X. So which implies intersection I equal to 1 to n U alpha I belongs to tau. So tau satisfies all the properties of a topology. Therefore this tau, what is this tau here? Actually P of X, power set of X, is a topology on X. We know that topology is a collection of subsets of X. Since This topology contains all of its subsets. It is the largest topology among any topology that can be defined on X. So this power set topology is the largest topology on X. It is the largest topology on X. It is the largest topology on X. Now, we will see another example for a topological space, that is indiscrete topology. Indiscrete topological space. So for that, let X be a non-empty set. I define tau as collection. It contains only two elements that are subsets of X, which is nothing but the trivial and improper subsets, empty set and X itself. Then we can easily prove that tau is a topology on X, because by definition itself, empty set and full set belongs to tau. So first two axioms are verified easily. Now for the third axiom, it should be closed under arbitrary union. Since the collection contains only two sets, there we need only check their union and their intersection. What is empty set union X? That is X itself, which is clearly contained in tau. And empty set intersection X, it is nothing but empty set, and it is clearly contained in tau. Tau trivially satisfies all of these axioms. Therefore, tau is a topology on X. And this topology is called indiscrete topology because it is actually exact opposite of the discrete topology. Because discrete topology contains all of its subsets and the indiscrete topology contains only trivial subsets, trivial and improper subsets. And I can say that it is the smallest topology among any topology. It is the smallest topology. It is the smallest topology on X. And X together with this topology is called indiscrete space. Indiscrete space. Similarly, I can say that X with the power set topology is called a discrete space. Discrete space. Okay. Now let's see some particular examples of topology. Take X as a set, one element set A. And I define a topology tau. Discrete topology first. Discrete topology I defined by tau D. Okay, I denote by tau D. Tau D is discrete topology, that is a power set topology. Okay, for convenience I represent it as by tau D. Okay, and what are the elements of power set here? Empty set and capital X. Capital X is nothing but the singleton set A itself. These are the only two subsets of the given set X, right? So which is the power set topology or discrete topology. Discrete topology consists of only two elements here. Both are empty and full set. Okay. And what is indiscrete topology here? We can define indiscrete topology. I denote it by tau I only for the notation, which is equal to collection, empty set and full set itself. And it is nothing but tau D. Here discrete topology and indiscrete topology coincides. Okay, and can you define any other topology for this set? No, because it contains no other subsets. Therefore, the only topology we can define on a one element set is discrete topology, which is same as indiscrete topology. Therefore, for this set the topology is unique. For a singleton set, there exists only one topology on it, can be defined on it. Only one topology on it. Okay, now I consider some two element set. X is equal to set A comma B, and we will see what are the topologies can be defined. First I define tau D, power set. What are the elements? Empty set, full set and the subsets singleton A, singleton B and AB itself, right? These are the four subsets of AB. Therefore tau D is a topology. Another is indiscrete topology. Here indiscrete topology is X and full set. What is the full set? AB. Okay. So both are different topologies here. And I will define one more topology TO1 as empty set and singleton A only, which is different from discrete and indiscrete. And I will define TO2 as empty set and singleton set B. So all these four topologies, we can check TO1 is a topology or not. Empty set belongs to X. Oh, one more full set should be belongs to this topology, right? So we need X. Here also X. So TO1 is a topology, TO2 is a topology because their union and intersections also belongs to TO1 and TO2 itself. So these are the four topologies can be defined on a two element set AB. Okay, and these two topology TO1 and TO2 are actually called Sierpinski topology. Sierpinski topology. These are the special topologies. We have to remind it for later. Now, every set, as a note you can write down as every non-empty set can be considered as a topological space. Considered as a topological space. Why? Because by defining either you can define the by defining discrete or indiscrete topology on it. Discrete topology or indiscrete topology. So by defining some appropriate topology, I can define I can consider every set as a topological space. Another example is every metric space is a topological space. Every metric space is a topological space. Why? Because metric space consists of open sets, and when you take topology as a set of all open sets in the metric space, it itself satisfies all the properties of a topology, and the topology is actually called metric topology. Metric topology, which is the topology on the metric space, which consists only open sets in the corresponding metric space. Okay, so these are some basic examples of topological space. Now we will see one important topological space, another example, which is called a cofinite topological space. Cofinite topological space. So to define a cofinite topological space, first of all I need a infinite set. Let X be an infinite set. Let X be an infinite set. Okay, and I define a topology which is called actually cofinite topology TO, which has nothing but empty set union collection of all A subset of X such that complement of A, I denoted by X minus A. Okay, complement of A is finite. Actually this kind of subsets are called cofinite subsets of X. When you have an infinite set and any subset of capital X whose complement is finite is called a cofinite subset. So this collection topology is nothing but set of all cofinite subsets together with an empty set. Okay, and we can prove that this TO is a topology on capital X, and this topology is called cofinite topology, and X together with this topology is called cofinite space. Cofinite space. Okay, and what is a cofinite set? Cofinite set in X are the subsets of X such that its complement is finite. complement is finite. Okay. Now, what is the advantage of taking X as an infinite set to define this cofinite topology? If X is a finite set, suppose that if X is a finite set, then any subset of X is always finite, right? A subset of X will be finite, and its complement X minus A is also finite for every A, also finite. Therefore, every subset will be cofinite set. Then there is no point of taking only cofinite subsets to make a topology. That's why we are taking infinite set to define a cofinite space. Okay. Now we will prove this tau is a topology. Okay. So claim tau is a topology. So we have to verify 4 axioms. First one, empty set should be belongs to tau. By definition of cofinite topology itself, cofinite topology itself, empty set belongs to that collection. By definition itself. By definition. And second one, full set should be belongs to tau. So to prove X belongs to tau, we have to prove X is a cofinite set, because the collection tau contains only empty set and cofinite sets. Okay, so when X belongs to tau, only when X is a cofinite set. So how will you check X is cofinite or not? We have to check its complement, right? So what is complement of X? It is nothing but X minus X. What is X minus X? Empty. Empty set can be considered as a finite set, right? It's a finite set because it has no elements. When X complement is finite, X is cofinite subset of X. X is a cofinite subset of X. When X is a cofinite subset of X, X automatically belongs to the collection tau. So tau contains empty set and tau contains the full set. Now we have to verify tau is closed under arbitrary union and finite intersection. For third property, let collection U alphas are belongs to tau. What it means? Each U alpha belongs to tau. So which implies U alpha is either empty or cofinite. Okay, we have to verify tau is closed under arbitrary union. For that, we want union alpha U alpha belongs to tau. This is our claim. That means union alpha U alpha is a cofinite set. Then only it can be belongs to tau. So you consider the complement of union alpha U alpha. What is that? X minus union alpha U alpha, which is equal to, and what is X minus union alpha U alpha? It is nothing but union alpha U alpha, the complement. And by using the properties of set theory, it can be written intersection alpha U alpha complement. And what do you know about U alphas? U alphas are the members of tau. When U alpha is a member of tau, either it is empty or it is a cofinite set. Now I am taking U alpha as a cofinite set. When U alpha is cofinite, its complement will be finite, correct? A set is cofinite if its complement is finite. So when U alpha belongs to tau, U alpha is cofinite, therefore U alpha complement will be finite, right? Since U alpha belongs to tau implies U alpha is a cofinite set, which implies U alpha complement. This C stands for complement, okay? U alpha complement is finite set. When all this U alpha complement is finite, intersection alpha U alpha complement is finite. Intersection of finite sets is again a finite set. Is finite set. When intersection U alpha complement is a finite set, intersection alpha U alpha complement can be considered as a cofinite set. It's a cofinite set. When it is a cofinite set, it automatically belongs to our tau. So what is this intersection alpha U alpha complement? This is nothing but x minus union alpha U alpha. So whenever x minus union alpha U alpha is a cofinite set, that union alpha U alpha automatically belongs to tau. Yes, intersection alpha U alpha complement is a finite set. Therefore, there is a mistake here. Therefore, union alpha U alpha is a cofinite set. Whenever its complement is finite, that set will become cofinite set. Here the complement is finite. Therefore, that set union alpha U alpha is cofinite set. Therefore, union alpha U alpha is a member in tau. Therefore, tau is closed under arbitrary union. Okay. Now, at last, we need to verify the last property of the topology, that is tau is closed under finite intersection. Now, to prove tau is closed under finite intersection, the last property. So, for that, let collection U alpha is a member of tau, which implies each U alpha is cofinite set. So, which implies when each U alpha is cofinite, we need to verify tau is closed under finite intersection. So, we have to check intersection I equal to 1 to n U alpha I belongs to tau. This is our claim actually. For that, we have to say this set is cofinite. When we'll say this set is cofinite, their complement is finite. So, we will consider their complement. What is the complement of intersection I equal to 1 to n U alpha I? That is intersection I equal to 1 to n U alpha I the whole complement equal to union I equal to 1 to n U alpha I complement, which is equal to when each U alpha I is belongs to tau, each U alpha I complement is a cofinite set. That means it is a finite set. When this complement is a finite set, finite union of finite set is finite, right? Therefore, this is a finite set. So, which implies intersection I equal to 1 to n U alpha I. When complement of a set is finite, that set is called a cofinite set. When the set is cofinite, it automatically belongs to tau. So, here complement of this intersection is a finite set. Therefore, this intersection will be belongs to tau. Therefore, tau is closed under finite intersection, which implies tau is a topology. And this topology is called a cofinite topology. And this X together with this topology is called a cofinite space. Okay, cofinite space. In a similar manner, we will see another example is a co-countable topological space. Co-countable topological space. For a co-countable topological space, we need an uncountable set. Let X be an uncountable set. When the set is not uncountable, then automatically every subset will be belongs to our collection. That will be lead to the power set topology itself. Okay, that's why we consider an uncountable set. Now, I define tau as empty set union co-countable subsets of X. Collection of all A subset of X such that A is co-countable. What is a co-countable subset? A set A is called co-countable if its complement A complement is countable. Actually, which is similar as same as cofinite topology. So So in a similar manner of cofinite topology, we can prove that by definition itself empty set belongs to our tau. And second one, what is X complement? X complement is equal to empty. This empty set belongs to tau, which implies X belongs to tau. X complement is empty. Empty can be considered as a finite set. Therefore, X itself is a co-countable subset of X. Therefore, X belongs to tau. Okay. And third one, tau is closed under arbitrary union. When you have U alphas belongs to tau, then each U alpha is a co-countable set. Then their union alpha U alpha is nothing but intersection alpha U alpha complement. Each U alpha complement is countable and intersection of countable set is countable. Therefore, this set is countable. Okay. Actually, its complement. Its complement is equal to intersection alpha U alpha complement, and it is a countable set. When it is a countable set, the union alpha U alpha belongs to tau. Union alpha U alpha complement is intersection alpha U alpha complement. It is a finite set, sorry, not finite, countable set. It is a countable set. Therefore, intersection of countable set is countable. Therefore, the whole thing is a countable set, which implies union alpha U alpha complement is countable. Union alpha U alpha complement is countable. Therefore, union alpha U alpha is a co-countable set. Co-countable set. When it is a co-countable set, it automatically belongs to our collection tau. And for the last property, we have to verify finite intersection. Intersection I equal to 1 to n U alpha I, whether it belongs to tau or not. For that, we consider its complement. Its complement is nothing but union I equal to 1 to n U alpha I complement. Again, we know that each U alpha I is a co-countable set. Therefore, its complement is a countable set. It is a countable set. And finite union of countable set is again countable. So, therefore, the whole thing is a countable set. When the whole thing is a countable set, complement of some set is countable. When complement of some set is countable, that set will become co-countable. So, which implies intersection I equal to 1 to a U alpha I is countable. Sorry, co-countable. Co-countable. So, when a set is co-countable, it automatically belongs to tau. Therefore, intersection I equal to 1 to n U alpha I belongs to tau. Therefore, tau satisfies all of these properties. Therefore, tau is a topology, and this topology is called co-countable topology. And the space X together with this topology is called co-countable space.